Hello all and welcome. Today we're going to do an introduction to inverse trig as functions. In a previous life, you have hopefully solved problems like this. You're given some kind of right triangle and two sides and an angle, and you're asked to solve for that angle. And the general approach that you probably used is something like saying, well, I'm given the opposite and the hypotenuse, so I can write that sine of theta is equal to 5 over 10, and then you can find theta by doing this inverse trig function, that it solves for the angle. So you could write that the inverse sine of 5 over 10 should be equal to theta. We've done this in geometry, right? This is how you solve for angles given any kind of side lengths, and you can do inverse tangent or cosine or any other function you want. So I think I'm in degree mode here. Just a quick check. Yeah, we're in degree mode. So we can just check that in the calculator. You have to go second sine. You get sine inverse. We could do 5 over 10. We get 30 degrees. So that means that 30 degrees is equal to theta. Now that should hopefully be no surprise to you, because what is 5/10 except 1/2? And from our unit circle studies, we know that when sine of theta is equal to 1/2, we're looking at a 30-degree angle, or in radians, a pi over 6-degree angle. So that's what we previously know is how to use inverse trig, and from this, we have this key idea that, well, normal trig takes in angles and outputs sides. Inverse trig has the opposite relation. It has inputs of sides, and it has outputs, angles. And in this sense, it works much like an inverse function should. You're exchanging the inputs and the outputs, or in the language of Math 4, you're exchanging the domains and the ranges of the two functions. Now that's all well and good for triangles, but what the heck do you do when you have something like tangent inverse of -1, which is not a side length that should appear in a triangle? Well, at first you might say, hey, no solution. That's probably what the you of, a couple years ago would have done. But the you of today knows better. Because the you of today knows that if tangent inverse of -1 is going to equal some angle theta, then it must be true that the tangent of that angle theta must equal -1. And then you could say, well, hey, maybe that's -1 over 1. And then you could start to go to the quadrants and actually find some triangles that have those solutions. So maybe you'd say, hey, well, that can't be in quadrant 1, but what if the x is -1 and then the y is 1? So we're actually looking at an angle right here, which would be in radians. We're going to switch to radians now, by the way, of 3 pi over 4. Because we have, here I should write it like that, a triangle there that could work. No, I'm doing a little scaling of 1 square is 2 markings here. And then you might say, okay, so the answer is 3 pi over 4. But then you might say, well, wait a minute. Couldn't there be another answer? All the way over here, where we also have a side of 1. Here, the x could be 1, and the y could be -1, and then the angle would be something like 7 pi over 4. So you'd say, well, okay, so there's two answers. Theta must be 3 pi over 4 or 7 pi over 4. But then you might go to your calculator. And you might put it in radians, because we're going to live in radians now. I mean, we could be in degrees, but we're going to be in radians. And nothing would change except the numbers we give. And then we could do tangent inverse of -1 and hit enter. We get, what the heck? Well, and then I think, maybe I need to convert that to pi. So maybe that's negative pi over 4. It is. So somehow we came up with two possible answers, but the calculator has a third answer, which is, by the way, the answer that is considered correct of negative pi over 4 is the only correct answer to this question. So how, why, what could be going on here? Oh, and just to prove something to you, there's nothing special about being in radians. This is not an issue that has to do anything with radians. I can be in degrees here, and I can do tangent inverse of -1, same problem. And I get -45 degrees instead of positive 330 degrees, 315 degrees. So it's not an issue of degrees and radians. It's an issue of how these inverse functions are defined as functions and how they're programmed into the calculator. And that's the main idea that we have to learn in this section, is how are these things created and how do they exist outside of quadrant 1, outside of triangles, in this coordinate geometry land that we're doing with trig. How does inverse trig work? So before we go any further, there's a really important note on notation here. Sine inverse, cosine inverse, and tangent inverse use these little -1 things. That is the inverse symbol, like when I write f inverse of x, I mean the inverse function of f of x. This is not the same as reciprocal functions, right? This is not the same as 1 over f of x. It's not the same as secant, cosecant, or cotangent. Completely different things. The inverse function here is switching the inputs with the outputs. So where we had sine of theta, I'm going to use the quadrant definition. Sine of theta is defined as y over r. Sine inverse of theta is not r over y. That's cosecant. It's actually sine inverse of y's over r's equal angles. That's the sort of correct definition for sine inverse. Now, this is terrible notation. That -1 has been used and abused way too many times in math. So one thing you might see, I will probably use it from time to time just to keep you on your toes, but I know our book uses like a mix of both, is instead of writing sine inverse with that -1, they'll write arc sine and arc cosine and arc tangent to mean the inverse functions. That's just to keep them from being mixed up with the reciprocals. And the reason is they use this as this prefix arc. In inverse trig, we're solving for angles, and we remember from like when we learned about radians that angles and arcs are kind of related in radians. So that's the idea there, is they're saying arc is kind of a word for angle there. So you might see that it's not a different function, it's just a different way of talking about inverse trig without using the -1 notation. I think the best way to think about an inverse trig statement is as a calculator or computer command, except in this case, or in most cases, you are the calculator or computer. But just like a calculator or computer, you're being commanded to do one thing. You're being commanded to find a single answer. So when you see cosine inverse of -√3/2, what this means is that you are being asked to find some angle, which we'll call theta, so that the cosine of theta would equal whatever's on the inside, in this case, -√3/2. So you can turn a cosine inverse or an inverse trig statement into a regular trig statement with a missing angle, and that's usually a productive way to solve it. But here's the catch. There are infinitely many such solutions to the equation cosine theta equals -√3/2. They're in this quadrant and that quadrant, but then you could also go around the circle the other way, or you could go infinitely many times. You could think about it as the cosine graph is a wave. It's going to hit -√3/2 infinitely many times. Well, for a calculator or computer, that's pretty miserable. Right, if I do this on a calculator, we need to only get one answer. We can't get multiple answers from a command like this. And in fact, we do. So we kind of need to understand, like, what and how does this calculator that is also us, how does it decide what number to give back? How does it know? And the key catch, I guess, is that inverse trig commands are thought of as functions. They only are allowed to have one output for each input. So there are specific rules about the angles that you are allowed to output. And we're going to think about these as range restrictions on the inverse trig functions. So we're going to go through the three inverse trig functions, sine, cosine, and tangent, and look at the range restrictions for each and give a couple examples of how that works out in practice. All right, so we're going to start with inverse cosine because in some ways it's the odd one out. So we're going to start with it. And you can think about cosine inverse as the thing that finds angles. So we know if cosine of theta is defined in coordinates as x over r, then cosine inverse has to take in x over r's and output angles theta. Now, the domain of cosine inverse then is all possible sort of legal x over r values, and that's any value from -1 up to 1. You can do cosine inverse of any number between -1 and 1 because those are the perceivable x over r's. For the range, though, there is a restriction. For inverse cosine, you are only ever allowed to output values between 0 and pi, including pi. You will never output numbers outside this interval when you're doing inverse cosine. So this is something you should absolutely be writing down if you haven't been taking notes yet. This you must write down and you must know. Put it on a flashcard, learn it, whatever you need to do. These range restrictions, they're not something you're going to be able to figure out on your own. This is just how the functions are defined. You have to know it. All right, so example 1, we're going to evaluate inverse cosine of root 2 over 2. So the way we do this is I first rewrite this as this is equal to some angle theta. So then the cosine of that angle theta must equal root 2 over 2. Now, this is where I think about my unit circle. And I think, what angles had cosine equal to root 2 over 2? And I remember that that was the 45-degree angles, the pi over 4s. But I don't have 4 answers here. I only really have 2 answers, because this is actually positive root 2 over 2. And cosine is positive in the x quadrants. So I'm going to delete those answers and just think about the angles in the positive quadrant, so pi over 4, and we don't usually give big angles here, we usually give negative angles instead, so negative pi over 4. Those are the 2 possible angle answers, the candidate answers, we call them for this equation. However, we're doing inverse cosine, and inverse cosine has this restricted range from 0 to pi. And only one of those 2 angles, even though there's 2 possible solutions, is within the range from 0 to pi. And that's pi over 4. Because negative pi over 4 is not in 0 to pi. So even though it's a solution to the equation, it's not an answer to this specific command, cosine inverse root 2 over 2. So I report back the only answer that was in the range I specified, pi over 4. Cosine inverse of root 2 over 2 is pi over 4. Now, a related question, I've just taken the other one and thrown a negative on there, but this throws us into like weird quadrants, and that's where things get complicated. So, same deal. I think, okay, the cosine of what angle theta would give me negative root 2 over 2. And I think again, this is asking me about the 45-degree angles, the pi over 4s. However, it's negative, and cosine's negative in the left 2 quadrants because cosine is the x over r, or x coordinate. So I think, what are those 2 angles? Well, the first angle would be 3 pi over 4, and the other angle that solves this equation would be 5 pi over 4. So it's really important, by the way, as you're doing this to like know your unit circle pretty well. If it means as you start you're looking at a physical diagram of the unit circle, fine, so be it. But if you want to do these efficiently, you really need to know your unit circle angles forwards as well as backwards. All right, so we have 3 pi over 4, 5 pi over 4. However, I need to pick one of these to answer. I can't give 2 answers. I need to give one single answer on this line. And I have a rule for inverse cosine that the answer needs to be between 0 and pi. And the only answer that's actually between 0 and pi is 3 pi over 4. 5 pi over 4 is outside of the range of this function. The answer is 3 pi over 4. It looked like a fraction for a second. It's not a fraction. The range must be between 0 and pi, which is what 3 pi over 4 is. So make sure you have this written down for inverse cosine. You have that range restriction. Its domain is important too, but more importantly is that range restriction. And notice how that restriction came into play when we were solving for angles in quadrant 1 or quadrant 2. And one way to think about this is that cosine inverse is defined to give answers in quadrants 1 and 2. That's the 0 to pi. So it's kind of the top two quadrants, and you have one positive quadrant for cosine and one negative quadrant for cosine. All the answers to inverse cosine will always come from those two quadrants. Let's take a look at inverse sine questions now. So if we have sine inverse of x is going to equal some theta, then, well, let's think about what sine was. Sine of theta was our y over r's, so sine inverse has to take in y over r's and output thetas. So the domain of sine inverse is going to be any valid y over r's, and just like for cosine, those are any values from -1 up to 1, because those are all the possible y over r's that you could ever have on a unit circle. The range for inverse sine, and again, this is important because it's different, it's restricted, is going to be from -pi over 2 up to pi over 2. Or in degrees, that's -90 to 90. This is weird, by the way, just to say. This is weird. What this means is that whenever you're doing an inverse sine question, you're only going to answer angles in quadrants 1 and 4. And when you answer an angle in quadrant 4, you're going to give it as the negative version of that angle. It's kind of like, it's a way of giving the smallest answer, the smallest, simplest answer. Even though it's negative, it's still going to be like a nice small angle. So, very important range restriction here. Let's see how this comes into play in a trig problem. So we're doing sine inverse of 1/2. So this is saying, okay, there's some angle theta where sine of theta is equal to 1/2. I think carefully about the unit circle, and I remember that there are two such angles where sine of theta is 1/2. There's actually, well, right, if I think about positive and negative, think about 4 angles where the opposite is 1 and the hypotenuse is 2. And that angle is pi over 6. Right, and like the pi over 6 reference angle in all the different quadrants. But this sine theta is positive 1/2. So where would the two quadrants be where that's positive? Well, it would be in the first quadrant or the third quadrant, because I would also have an opposite of 1 and a hypotenuse of 2 there. So the two candidate answers are 5 pi over 6 and pi over 6. However, the restriction for sine inverse is it has to be from -pi over 2 to pi over 2. 5 pi over 6 is outside of that restriction. So the answer that we're going to report is pi over 6 only. That's the only answer we're going to report for this problem. Let's evaluate sine inverse of -1/2. So this is saying there's some angle theta where the sine of theta is equal to -1/2. I again think about the unit circle, and I think about those 30-degree or pi over 6 angles, but now I'm thinking about 30-degree or pi over 6 angles down in quadrants 3 and 4, because those correlate with y being negative. So I'd have like a -1 over 2 here and a -1 over 2 here. So those angles would be, well, this first angle that I draw, that would be 7 pi over 6. And the second angle I draw, I'm going to go, the shortest distance around, so we're going to say that that's -pi over 6. Instead of going all the way around to 11 pi over 6, we're going to say -pi over 6. Because I'm trying to evaluate sine inverse. I'm not just trying to solve this equation. And I know that this has the range -pi over 2 up to pi over 2. Only. That's the only range of answers I'm allowed to give for this function. So of these two answers, 7 pi over 6 is not within that range, but -pi over 6 is. So I'll report the answer -pi over 6 for sine inverse of -1/2. And here is the sine inverse everything together. Again, if nothing else, you're writing down, at least make sure you know this range restriction for inverse sine function. The last inverse trig function that we really care about is inverse tangent. So in coordinates, tangent of theta is defined as y over x. So the inverse tangent will take in y over x's and output angle thetas. Interestingly, that means that the domain of inverse tangent is actually all real numbers. Ooh. Negative infinity to infinity. Because y over x can be around, as you travel around the unit circle, that can actually be anything. And that matches with the idea that the tangent graph goes all the way up and all the way down. So the domain of inverse tangent is anything, but the range is exactly the same as inverse sine. It is restricted to negative pi over 2 to pi over 2. That is quadrants 1 and 4. And if you're in quadrant 1, you're going to give a positive answer. And if you're in quadrant 4, you're going to give a negative answer. That's how it is for inverse tangent. It's the same as inverse sine in terms of range restriction, not like in terms of the whole function or how you solve things, just in terms of range restriction, it's the same as inverse sine. So as we solve these out, to choose our answer, the correct answer that we want, we're going to look at this particular range for inverse tangent. All right, so hopefully this should be familiar to you. You might even want to pause the video and try these problems ahead of me. But when I see tangent inverse of root 3, I'm thinking of some angle, tangent theta, where that theta, that is equal to square root 3, and I'm going to write it as root 3 over 1 because I'm trying to help myself think about a unit circle angle. And that would be something where the y is root 3 and the x is 1. So where would that be? Well, on the unit circle, in the first quadrant at least, I know that triangles that look like this have a hypotenuse of 2, which I don't care about, but they have an angle of pi over 3. So that's one of the possible answers. But I know also that this is a positive root 3, so I could also have negative root 3 over negative 1 and get the same result. So there's also a candidate answer down here in this quadrant, where I have negative root 3 and negative 1. So the two potential answers, or candidate answers, the two potential thetas are pi over 3, and this one would be 4 pi over 3, the two answers that I could have. However, I'm not solving this equation, I'm evaluating inverse tangent. And when I evaluate inverse tangent, I'm only allowed to report the angle that's within that specified range, negative pi over 2 to pi over 2. So the only answer I should report is the first quadrant angle, pi over 3. Since the other angle was outside of the quadrants that are part of the range restriction for inverse tangent. All right. So for inverse tangent of negative root 3, again, I'm thinking negative root 3 over 1, so this would be some place where tangent of theta is negative root 3 over 1. Well, there's two possible places that could be. Either the adjacent is negative 1 and the opposite is root 3, or the adjacent is 1 and the opposite is negative root 3. So there's two ways to find the candidate answer. I think back to my unit circle, and I remember that this must be 2 pi over 3, and this one must be negative pi over 3. So my possible answers, or what I'm calling the potential theta, or results, are 2 pi over 3 and negative pi over 3. However, for inverse tangent, the rule is that it has to be in quadrants 4 or 1, and specifically between negative pi over 2 and pi over 2. So I'm going to cross out that answer because it's not in that range. I'm going to select negative pi over 3. And report that that is the answer I desired. One note, like important note, by the way, because this will cause you to get problems wrong. Even if you select and say, hey, this is also 5 pi over 3. If you report that the tangent inverse of negative root 3 is 5 pi over 3, that's incorrect. Even though you're talking about the same angle in the same fourth quadrant, 5 pi over 3 is not within the specified range. And the whole point of inverse tangent, inverse trig, is that you are computing a command. You're trying to think exactly like your calculator. And if I'm in radians, so I do tangent inverse of negative root 3. Whoa there. I'm not going to get 5 pi over 3. I'm going to get this, which I know is the same as negative pi over 3, because it's a little more than 1. So the whole point of this is basically predicting what answer your calculator will give you, which means you have to follow the rules of those domain restrictions, like to the letter. So here's all the work for inverse tangent in 1. And again, specifically, the thing you really need to know about this inverse function, other than kind of generally how to use it, is the range restriction, negative pi over 2 to pi over 2. Answers will always be within that range. So just to quickly recap, inverse cosine has a range restriction from 0 to pi. Inverse sine has a range restriction from negative pi over 2 to pi over 2, quadrants 1 and 4. And inverse tangent has the same restriction, negative pi over 2 to pi over 2, quadrants 1 and 4. But it's inverse cosine that's different, where you should report answers in quadrants 1 and 2 instead. So this is kind of mysterious. Like, why do these restrictions, why are they? Why is cosine different? What's going on? I want to try to explain this, and to explain it, we need to think back to chapter 1 when we first learned about inverse functions, and we need to think back to the graphs of these three trig functions that we are trying to find the inverses of. And the key idea is this. An inverse function can only really be defined when its non-inverse function, its forward function, passes the horizontal line test. Because the inverse function is going to be a reflection over y equals x of that function. So for the inverse function to be a function, the original function has to pass the horizontal line test. Now look at this graph of cosine. It very much fails the horizontal line test, like very, very badly, right? Like, look at all those places where those two horizontal lines intersect, which means that by all rights, inverse cosine should not exist at all. And it's weird that it even does. But back in chapter 1, one thing we did is restrict the domains of the forward function so that we could create an inverse function. And when we restrict the domains of sine, cosine, and tangent, we're going to end up restricting the ranges of the three inverse functions to exactly what we just learned above. So this is a graph of y equals cosine x. And thinking about the graph of cosine, we need to sort of take this function and select only part of it that is passing the horizontal line test. Well, I want to select as most of the function as possible. So I'm going to start at 0 right here and sort of shade in the function until I get to a place where I turn around, where I would start to fail the horizontal line test. Well, where do I start to fail that horizontal line test? Right here. That is, if I shaded in any more, I would start to go up, and then I would fail the horizontal line test. Well, look at that. That's from 0 all the way up to pi. So that's a domain restriction of cosine, which turns into a range restriction on inverse cosine. So that's why inverse cosine is restricted from 0 to pi. If we went any further to the left, well, we'd be failing the horizontal line test again. So we've gotten like the most we can out of this. Also notice that when we have this little restriction, it also has a range from -1 to 1, which was the same as our domain of inverse cosine. Let's take a look at y equals sine of x. I'm just going to try the same thing as I did with cosine. Let me start at 0 and start shading function all the way up to pi. So I'm going to go all the way up to pi. La 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 la, happy day. I'm out at pi. oh no, I've shaded a portion that fails the horizontal line test. Well, that's no good at all. So I have to delete some of this. I can't go as far as pi. In fact, I can start at 0 and I can shade all the way up, but I can only really shade up till the top here, which is at pi over 2. But if I shade backwards, I can continue shading backwards, sort of selecting this part of the function until I get back to negative pi over 2. And this is the longest such interval that passes the horizontal line test. If I went farther in either direction, I would start to fail that test. And this is also the interval that includes 0, which is of course nice, right? We want like sine inverse of 0 to behave like we expect, so we want to do that. And so we end up with quadrants 1 and 4. And that's why inverse sine has a different domain restriction than inverse cosine, because if it was defined in the same quadrants as inverse cosine, you would not be passing that horizontal line test. Now let's look at tangent. This is the graph of y equals tangent x. Now, technically, you could actually pick any sort of chunk of tangent and have it work out, but it sure seems like the most logical chunk of tangent to shade would be one full period centered around 0. That is the largest such piece that passes the horizontal line test, right? But if I went any further, I would then fail the horizontal line test. So this is the largest such piece that does that. And where does that piece start? Negative pi over 2. And where does it end? Positive pi over 2. So that's why inverse tangent has the same restriction, because we restrict tangent to negative pi over 2 up to pi over 2. Now, technically, is this super useful to know? No, not really. The domain restrictions, of course, you need to know. But the graph part is just explaining why they are exactly what they are in hopefully sort of a graphically useful way. So what do you need to know coming out of this video? You need to know the domain restrictions for inverse cosine, inverse sine, and inverse tangent, and how to do problems like any of these 6 problems. You use your draw triangle, you think about your unit circle, you answer based on the domain restrictions. There are more complicated problems to do, but we're going to cover those in another video. So, at this point, thank you all for watching, and we'll see you next time.